my favorite scientist, looking back in history, is Ibn al-Haytham, who is also known as Al-Hazan. History of physics in Pakistan is old, definitely.
Why is Bose-Einstein condensation seen as such a breakthrough in modern physics?
Understand those things from their mechanical motion to internal origin of mass and so on. So it's a large subject, and that gives a very big inspiration to understand, to learn.
Assalamu alaikum wa rahmatullahi ta'ala wa barakatuh. Hello everyone. My name is Mustafa Hussain and this is COMSTECH podcast. Today we have a special guest, Professor Farhan Saif from Qaid Azam University.
Assalamu alaikum. Well, thank you very much for inviting me here. It's a very beautiful experience sitting with you and talking about my experiences, my work and my future endeavors. So I submit my thanks for inviting again.
Professor, thank you very much. What is the first thing that comes to your mind when you hear the word physics?
It's a subject which immediately brings you to practical issues in real life. So, and especially we talk about the nature, we want to understand from the smallest scale to the largest scale, and then we see things around and understand those things from their mechanical motion to internal origin of mass and so on. So it's a large subject, and that gives a very big inspiration to understand, to learn. So that it is requiring skills related to mathematics, computational, computer science, statistics. So many combinations of subjects are necessary to understand once you talk about physics.
Is it truly possible to understand quantum physics?
Well, you see, quantum mechanics is a new subject, and people have big excitement into this subject. And still, there are open questions from the interpretations to the newer information coming into the subject. So this, as a young student and a researcher, almost everybody is baffled, is surprised. Because one has to really develop newer concepts and understanding. And this journey goes on till you are even you say that you are an expert, but you have to really keep yourself aligned with the newer ideas, newer approaches, and newer understandings which are coming around you. So this is something which is interesting.
And your new mathematics?
For example, in my work,
mathematics.
Newer mathematics, but newer applications and newer understanding. For example, in my new work, I have been working on heavy photon. Now, that heavy photon concept is a very beautiful topic because it is going to answer the missing mass into the universe, which we say that 95% mass is missing in the outer universe, and try to answer in various ways. So in this new work, I'm giving a solution, a possibility that where is the mass and how the mass is what mass is in reality, how we can really think of. So now this is a question which is requiring good discussion and always opens a good tabletop discussion.
How did your early studies in high school influence your decision to pursue your current fields of specializations?
In my early studies, it was very there was big emphasis on doing analytical work and also having some simple applied side examples. So real applied side physics were being taught. So I must say that a strong understanding of basic concepts which I developed in my early days helped me a lot once I was doing research. So and also my PhD and my later years working with my students and independent projects and so on.
That's exactly. How did Qaid-e-Azam University influence your research perspective?
Well, at Qaid-e-Azam University, there is a good opportunity that you can do research in any subject you like. And it's a big freedom, so that helps a lot. And another thing which when I compare with other universities, so we don't have that horrendous amount of teaching load. So that helps definitely because now here we can focus on real experimental and real research topics. In my scientific journey, I started my my early education. I would start from Qaid-e-Azam University because there is the subject where I learned physics as a major subject, major focus. And then after that, I went to Germany. I did my PhD from there. And that was a beautiful time because at that time there were many new discoveries were being made, especially in my subject, which is controlling of atoms using optical fields and applying towards quantum computing, quantum information, Nano-Science and technology. So these were very early days of these subjects. And from the theoretical point of view, I was working on newer disciplines like classical mechanics, classical chaos, quantum chaos, and so on. So those were very much useful things which I learned during my days in Germany. After my PhD, I went to various different countries like Italy, France, England, then Japan, and I spent one sabbatical in USA, another sabbatical in Brazil, and then one in Japan again. So these all experiences gave me the first-hand knowledge about the latest disciplines which are coming up, which are being taught, which are being discussed. So that's why I think this was quite helpful.
In what way did German discipline and Japanese precision changes your scientific mindset?
Well, in Germany, what I found, it is very much important to do the applied work. And so that meant that any topic which we are picking up, it must be having relation to the real life applications. And that that approach I kept during my later years when I was working as a professor, as an academician, and talking to my students and colleagues. In Japan universities, they are very much applied. They work on the applied topics, but they go one degree of they go one. Okay, they are more applied than Germans because their all effort is to help the industry. So they pick only those topics which have real direct connection to the industry. So that became also a very strong motivation for me as well. So I have kept that also in my work. In Germany, I remember that all our effort was to pick up the topics which are applied side topics. So they were having very good connection. In USA, for example, I was there for a year for my sabbatical. So I found that in US universities, you have more freedom to, and you can also work on the basic topics as well. So that means now fundamental physics topics, basic physics topics, they can also be discussed very frequently and very often. Well, when we talk about the German setup, so German setup is also very helpful in producing very good scientists today as well. In past, the German setup was uh, producing wonderful names, and we know them very well, like Einstein. He was very proud to be German. He always talked in German language and so on. So this is a very good connection. So we find that even in German setup today, there are new good names coming as well in your subjects.
How would you explain quantum optics to someone new to the field?
Well, in quantum optics, we actually discuss the interaction or application of light on matter. So this is the starting point. So whenever we want to understand the effect of light on matter and the other way around, we pick up the tools in the quantum mechanical domain. We consider matter at the smallest level in the form of atoms or molecules, and then we consider the field, either conventional field coming from any known source like sun or any lamp, or then we pick up some specially designed fields like quantum electromagnetic fields. So they are used to understand the effect of light on matter. So this is how we understand the quantum optics.
What changes when shifting from light optics to atom optics?
Okay, when we want to talk about the atom optics as a subject, so we control atoms using optical fields. So that means we set such conditions in which our optical field applies a force on atoms, and this way we engineer all different kind of controlling components like reflector, beam splitters, like interferometers, and doing experiments with atoms now.
What is quantum chaos?
It's a it has origin in classical chaos, and classical chaos is a discussion which comes from high dimensionality. In real experiments, when we work, so we normally work in the higher dimensions. This is one-dimensional, two-dimensional, three-dimensional. The word around is a three-dimensional word. And when any two dimensions are interacting with each other, affecting each other, or influencing each other, so that then we should expect system should be having a chaoticity. That chaoticity can be renamed as disorder or complexity. So the object which is moving around may be following some complex trajectory. So that would be a source of disorder and order discussion. So if in high dimensionality still there is some order, a repetition of some trajectory, that would be named as order. So this is a simple way of saying a complex dynamics. So now if we take this discussion to quantum mechanical domain, that if we have a particle, but that particle under discussion is a quantum mechanical particle, say it is an electron, it's an atom. So that implies that we are now performing a quantum mechanical analysis of classical system, which is chaotic. So this system or this discussion would be named as quantum chaos.
Where does chaos appear in system designed from perfect control?
Well, if we have a system with perfect control, so that implies that we have a control on the order dynamics. if there is some kind of perturbation, if some kind of external influence, and that takes that order dynamics to a disorder. That is the emergence of chaos. So this way we can understand.
Does quantum chaos create obstacles or open new possibilities for physics, for example?
Well, whenever we talk about quantum chaos, so actually we discussed a high dimensional system, a larger system, and now these larger systems have more controlling parameters. And those controlling parameters gives us good chance to introduce a better control in our system. So we can adjust those parameters, those controlling parameters as per our requirement, and we can introduce a control in that sense.
What is the historical development of the idea behind Bose-Einstein condensation?
Bose-Einstein condensation is considered as another state of matter. We obtain these states when our constituent particle are all behaving coherently. The simplest example, which was discovered first, is in optics in the form of lasers. We see that all photons which are making light are evolving in a coherent manner, and that is easily seen because all have the same wavelength. That means the same color, and all moving in one direction, because that's why we see laser spot on the wall. And then and the spatial coherence and the temporal coherence is useful in surgery, because we can apply a certain force and power at a particular point in a coherent fashion. Now, when we want to develop this condensate using atom, which was originally the idea of Bose, when we want to talk about the Bose-Einstein condensation with the help of atoms, that was basically we waited for a long time, because it was not possible to have atom in a two atom following a coherent dynamics, and that coherent dynamics was developed once we were able to achieve very low temperature for the atoms. So now when we bring the atoms to temperatures as low as microkelvin or nanokelvin, there we see the de Broglie wavelength, which is the wave nature of atoms, becomes as far bigger than the size of the atoms, and that makes them to be coherent with each other, and we see a coherent form of atoms all in one state. It was the work of Bose where he came up with this idea, and then Einstein contributed there, and they introduced their own distribution function for these.
On 1925, I think.
It was 1925. So in the very beginning, it was not considered useful, because experiments on helium were very much against this kind of condensation, because once we see helium is cooled down, so there is superfluidity coming in. So that was not showing any condensation. But after, as the thing proceeded, as the discussion kept on, so first the photons, which are bosons, they were developed in the condensed form, in the form of lasers, and then once it was possible to cool atoms to lower and lower temperature scales, it was possible to bring atoms in the condensed form.
Can you give us some example of applications of this idea?
Well, the simplest example is something like atom lasers, because now we have such sources of matter which can, from where we can have coherent source of de Broglie waves. And now this coherent source of de Broglie wave can be very useful in, for example, lithography, in chip making, in in any circuitry at a smaller scale. We want to develop one-dimensional wires and so on. So these topics, these one-dimensional, these 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 atom lasers can be very useful in these topics.
Does absolute zero truly exist in physics?
It is not possible.
It just
It doesn't
imagine
exist
it.
so far. But it is possible to bring it as low as possible. For example, microkelvin, then nanokelvin, then picokelvin, and even attokelvin. But attokelvin is already 0, 10 raised to minus 18 Kelvin, 10 raised to minus 12 Kelvin, 10 raised to 9 Kelvin, minus 9 Kelvin. So they are already 9 zeros after point. So we are approaching to 0 in that sense, gradually and gradually and gradually. At different temperature scales, we observe various different properties of matter. For example, at microkelvin, millikelvin to microkelvin scale, we see coherent atoms. They are cold atoms, but they move in a coherent fashion. But from microkelvin to nanokelvin, we bring these atoms to condensed form. And then below that, we can develop, to picokelvin scale, we can develop supersolids, which is another state of matter. So at every scale, we have various different newer phenomena which are coming. For example, at below nanokelvin scale, we enter into the discussion of newer materials which can be obtained only at that scales. So that is a cold atom quantum chemistry. So we can develop a newer kind of material at sub-nanokelvin scales. So those material can be used also in those on those temperature scales.
Why is Bose-Einstein condensation seen as such a breakthrough in modern physics?
Well, you see, first it's a milestone that we have achieved this, and then there is a excitement that we are in a position to develop newer kind of tools and devices. For example, there's a beautiful discussion which I had once with Professor Chu, and he was talking about. I was curious that why we want to bring the atoms to picokelvin scale, and his first comment was that it is possible to develop, for example, gravitational wave detectors. Because at present, the gravitational wave detectors are miles long interferometers. But his comment was that, perhaps at that scale, using a supersolid state of matter, we may develop newer kind of gravitational wave detectors. So there is an excitement that newer kind of devices can be made.
At what point does nanotechnology truly intersect with quantum physics?
Well, in quantum mechanics, in the quantum world, there is a big target to bring the discussion to macroscopic systems. That let me repeat it, that we want to control macroscopic systems in a quantum mechanical way. So now that brings a discussion to the nanoscale. For example, we want to have nanoparticles, we want to have nanomembranes, we want to have some setups which are larger scale objects, and they behave still in the form of quantum, what quantum mechanics predict. So this makes the nano technology very close to the quantum domain.
Is quantum informatics poised to become the next data revolution?
We are already seeing the quantum information entering into this scale, because our present day satellite communication is very fast becoming the quantum satellite based communication. What it means that all information which is being transferred from ground stations to the satellites is being performed using quantum mechanical ways, and the way the information is being spread to different stations on ground, they are all quantum mechanical. So that means that we have broken various different barriers of open space quantum communication. And then we have quantum cryptography coming into a very fast application stage. So various different countries are using quantum cryptography approach to send signals and to send data from one place to the other place. So this is becoming very fast, a very important component of our daily life.
What are the key differences between quantum computing and the classical computing?
Well, in quantum computing, we find that speed is very fast, the storage efficiency is very high, and then processing is very useful, very comfortable. And we see reversibility as one possibility, which is not there in the conventional systems. So these are various advantages we find in the quantum mechanical computing.
How do you see the contribution of Pakistan and other developing nations in this field?
I am in contact with various different experts in various different Islamic countries. I am visiting also some countries in near past, for example, Jordan, Uzbekistan, Morocco, and Egypt. And so I find people are very much keen to learn these new topics. And they have also good expertise. They are very good experts in sitting in those countries. So I think collectively we can have a good infrastructure where we can develop newer knowledge, newer applications, and devices even.
What is your favorite physicist?
My favorite scientist, looking back in history, is Ibn al-Haytham, who is also known as Al-Hazan. So he eventually brought the latest techniques which we use in physics, in expanding knowledge and developing knowledge. So his book was used for more than 1,000 years, and his discoveries was named after many other scientists who from West, and they presented their own. So that's again interesting thing, and so I think he deserves a good appreciation. And then in latest times, I would say Einstein is a good name. I think that's and Feynman is I appreciate. I have learned. I've read him a lot, and so.
Could you give us an overview of the history of physics in Pakistan and highlight some of its most influential figures?
History of physics in Pakistan is old, definitely. But the most major contribution or the most major presence is due to the Abdus Salam. So Abdus Salam, he was here in 50s teaching in a government college, and then he went back to England. But even from that time onward, he had some very beautiful personalities in physics as his students, like Riazuddin, Fayazuddin, like Kamal Saab, and so on. So there are many good names. And definitely he trained and he inspired many other people who were studying physics. So there is a good history of physics people in Pakistan, and in younger days, in present days, we see that there are good inspired people who want to contribute in physics. They want to contribute in the experimental side, theoretical side, in industry, and they're doing good, I think.
Who do you think might be the next physics Nobel Prize winner from Pakistan after Abdul Salam?
Well, when we want to talk about the second Nobel Prize in Islamic countries or in Pakistan precisely, so that may be not that far in future, because we are producing wonderful people. We are producing very excellent students, and they have all curiosity, they have all excitement to develop something new. Even though our resources are not that big as we see in the European countries or in America, even in Japan, they're investing a lot, and our investment is not that big. But I am very much confident that the way our people are developing their skills, their understanding, their motivation, it is not that far.
Thank you very much.